Thanks everybody, thanks for joining Experiment channel. This is the continuation of the first presentation for the heat transfer, and we are now going to see what is happening when the potato is getting cooled. Before we have seen the Newton's law, and now we are deepening this law. We are finding something in addition, and we will develop the Fourier equation, which is a little bit complicated with more mathematical steps in between, and I hope you will enjoy it. Let's start. We have seen the cooling of the potato by means of the experimental evidence and also using the Newton equation, and we find that there is something different. There is a discrepancy, so we want to deepen what is wrong now. And afterwards we go inside the potato and we will recognize that the temperature is also having a distribution inside the potato, which is following the Fourier equation. So we will try to develop a model for understanding it, and then we get the final confirmation by the experiment. In the first presentation, we have used the model developed by the Newton equation to find the law of cooling of a potato. So we replaced all the parameters, area, C, H, and temperature average to this final expression for the temperature in function of time. And we unfortunately get a curve which is not matching our experimental data, the red spots below. What is wrong? We have neglected an important way of heat transfer, which is the evaporation. The initial mass of the potato is 140 grams at the initial temperature 82.6 degrees. But after the cooling, after 2520 seconds, the mass of the potato is actually something smaller. So the potato has lost its weight 7 grams less. And those 7 grams are responsible for the heat taken out by the evaporation. The latent heat of the water from the literature is given. Eventually, we get 16,000 something more joule. But what is the total heat which is delivered from the potato to the ambient? Is given by this formula. It's 22,000 joule. So the major part, 73% of the heat, is given by the evaporation. So nothing to do with convection, neither to radiation. For sure, our formula is not matching. And to match our formula, we have to correct our H factor, the heat transfer, by using this corrective factor 1 over 27%, because 27% is the difference between 100 and 73. So H times 3.7. With this change, the formula below becomes this one in red. So the B factor is bigger, and our experiment data are fitting the curve. Now we make a step forward. The Newton law was assuming the uniform temperature of the body, so inside and outside same temperature, but actually the potato, it's a massive body, and the temperature is changing from the heart to the skin. And this is according to the Fourier equation. The equation is given by this expression, which is well known. K, the conductivity, is a new parameter we have introduced right now. Laplace operator of temperature equals C times density derivative of temperature over time. And in a spherical coordinate system, when the temperature is only depending upon radius, we can simplify the Laplace operator using this expression under brackets. And we introduce the diffusivity coefficient alpha, which is the ratio between the thermal conductivity K and the product between the specific heat capacity C and the density R. whose dimensions are square meters over second. This is a differential equation with partial derivatives, where the unknown function is temperature, depending upon two coordinates. One is a spatial coordinate, which is radius, and the second is a time coordinate. To solve, it is not so easy, and we need also to consider the boundary conditions. Space and time condition. For the space, there are two conditions. So for R0, the first derivative of temperature is 0. It means all the heat transfer is from the center to the outer part of the potato, and to the skin of the potato we can use the energy conservation, saying that the heat transferred to the skin by means of the conduction, the first member, is the same as the heat delivered to the ambient by means of convection and radiation. In this case, the area among the two members have been eliminated. And then we have the second condition for the time. It means at the initial condition, the temperature in the heart and in the skin of the potato and everywhere is the same, equal to the starting temperature. We can solve this only numerically. We need to approximate the derivative of the temperature over time with the delta T over delta R. As well, the second derivative versus R with the delta of above over delta R, and the derivative of the temperature versus time as delta T over delta time. In the second member, we see there are n suffix here. What does it mean? We divide the radius in n big space intervals. So this is the function derivative calculated at the single interval n. In case of spatial derivative, the n is changing. For the time derivative, the n is not changing, but the temperature is calculated between the time t and the time t minus delta t. And this expression is valid for n small between 1 and n big minus 1. The same equation we have seen, it is written now in a numerical way, like displayed here. And isolating t n plus 1, we can get this expression. We need now the boundary conditions. So t0 equals t1 and tn equals to this expression. They come both from the initial conditions if we use the numerical form. It means that now Tn, with n small changing from 0 to n big, is known at the time t, and then by iteration can be calculated at any following time. Let's see an example, always with the same potato. So the diffusivity is given by this value. The diameter is 16 millimeter, so the radius is a half. We decided to have 10 radius steps, and then delta t 30 seconds, and the initial temperature 83 degrees. We need the guess value. Let's assume 82 degrees for the initial temperature at the center of the potato. The T1 for the first radius step is the same for the boundary condition, and T2 is given by this iterative formula. We replace the values, we get this expression with the numbers, and T1 is the guess value, and T1 star is the initial temperature, 83, and finally we get 80.3 degrees. And T3 we can use the value of T2 right now, keeping always the same temperature at the time before, because we did not change the time, so 83 stays the same, and we get 75.7 degrees. And then we put remaining values always at the same time delta t. See the result of our iterative formula in the last row, referring to time 30 seconds for the different radius. But we notice that the values are becoming very strange, even negative values for the temperature. What does it mean? Actually, we forgot to use the second boundary condition. If we use the boundary condition for T10, we get for it a value which is minus 5,533, different from minus 20,825 displayed above. It means that we need to change the gas value, 82 degrees, till when the condition for a temperature at radius 10 is satisfied. We can use a tool like GoalSeek in Excel, and if we get the right gas value, eventually we find for the temperature at the skin of the potato the same value by using the iterative formula and by using the boundary condition displayed above, and then our values are correct. If we repeat the game for every row, we solve the question for every hour and for every time. So we have this table below. And we can display the corresponding charts. First, temperature versus time for different air values, like here. So the cooling at every radius is different. The inner part of the potato is cooling slower at the outer parts, as we can see. And the second is the temperature distribution at different values of the time. So here are displayed the temperatures inside of the potato, but for different times, starting from the upper part up to the lower, the time is increasing. What is interesting to notice, at the first beginning, the temperature is always the same, but also at the very end, the temperature is approaching to be the same, and the changes are happening only in between. We get a section at time 1080 seconds, and we notice the distribution inside of the potato. It's like the chart, and we can compare with our numerical simulation, which is fitting very well. For time 1320 seconds, and we observe the same, so the red curve is also fitting the experimental values got by the thermo camera. For time 1530 seconds, the blue curve is also fitting quite well the experimental values. Thanks everybody for attending, and thanks Joseph Fourier for your exceptional contribution. You are really a strong man.